how can we keep all of these functional groups organized? How can we keep all of the reactions of all of these functional groups organized? Stay tuned, because I'm going to try and convince you there are only 2 types of organic chemistry reactions in all of organic chemistry. Only 2? Don't believe me? Stay tuned and find out. Hey there, OChemNinjas. In a previous video, I took you on a tour of the major functional groups that you need to know for organic chemistry. If you'd like to brush up on those functional groups, I'll have a link to that video down below. In that video, I kept teasing that there was a reason why I put them in this particular grid in this particular arrangement. This is the video where I will reveal why I put them in this arrangement and why it's so useful for organizing organic chemistry. The reason I have these groups organized in this list is because they are arranged by oxidation level. You've probably heard of oxidation state before, where you take an atom and you calculate the oxidation state based on the electronegativities of all the atoms attached. We can do that for organic chemistry, it's just not very useful. For example, these alcohols all have different oxidation states. If you go through and calculate the oxidation state for each of these indicated atoms, they're all different, even though these are all kinds of alcohols. The carbonyl carbon in methanol has a -2 oxidation state. In ethanol, the carbonyl carbon has a -1 oxidation state. In isopropanol, that carbon is neutral, and in t-butanol, that carbon has a +1 oxidation state. And I gotta tell you, that's just not useful for organic chemistry. In fact, knowing that these alcohols have different oxidation states almost makes things more confusing. These are all alcohols. They're all unified by the same kinds of chemistry we can do to that functional group. So differentiating the oxidation state really doesn't help us organize these reactions at all. But oxidation levels is a very useful way of organizing your functional group. And under this system, all alcohols, regardless of their degree of substitution, are at the 1 CZ bond oxidation level. What do I mean by that? A Z group is a placeholder for any electronegative atom that's not carbon or hydrogen. It stands for a heteroatom. Organic chemists are very narcissistic. We like carbon, hydrogen's pretty cool, everything else is in other, everything else is outside, everything else is different. A heteroatom. Hetero, different, atom, atom, different, atom. And the alcohol is at the 1 CZ bond level because the carbon is attached to 1 heteroatom, 1 Z. 1 carbon heteroatom bond, 1 CZ bond makes it the 1 CZ bond level. Everything on this rung is at the 1 CZ bond level. The nitroalkane has the carbon attached to 1 nitrogen, 1 heteroatom. The thiol has the carbon atom attached to 1 sulfur atom. For each of these functional groups, we have a carbon bonded to 1 heteroatom. The one exception is the alkene. It doesn't have any heteroatoms, but chemically it still is at the 1 CZ bond oxidation level. It has that same kind of reactivity. At the bottom of this ladder is the 0 CZ bond level. That would be regular, boring alkanes with no heteroatoms attached. We have a variety of functional groups at the 1 CZ bond level, and even more at the 2 CZ bond level. At the 2 CZ bond level, we have a carbon with 2 heteroatom bonds. In the ketone, the carbonyl carbon is bonded to the oxygen twice. 2 CZ bonds. Same thing with the acetal. It's attached to 2 different oxygens, but it's 1 carbon with 2 CZ bonds. The epoxide's a bit of an outlier. It's 2 different carbons attached to the same heteroatom, but this functional group has 2 CZ bonds contained within the functional group. At the top is the 3 CZ bond oxidation level. These are carbons that have 3 bonds to heteroatom. The carboxylic acid has the carbonyl carbon bonded to the oxygen twice and the other oxygen once for a total of 3 CZ bonds. The acid halide has the carbonyl carbon bonded to the oxygen twice and the halogen once, 3 CZ bonds. And the nitrile has the carbon-nitrogen triple bond, so that carbon is bonded to that same nitrogen 3 times, 3 CZ bond level. And if you want to get cheeky about it, at the 4 CZ bond level, we have carbon dioxide. All roads lead to carbon dioxide because when you burn any of these things, the combustion product will be carbon dioxide. Although there are other legitimate functional groups at the 4 CZ bond level, we just don't encounter them in sophomore organic chemistry very often. Okay, so that's the setup. Why is it important? Well, pay attention because this is really cool. By organizing these functional groups in rungs of this redox ladder, we have organized them by their chemistry. And even better than that, we have organized them by how we can interconvert between these functional groups. If you want to move up and down the rungs of the redox ladder, if you want to move up the redox ladder or down the redox ladder, you're going to be using redox chemistry. Each rung of the redox ladder is a higher oxidation level, so if you want to move up the redox ladder, you're going to need to be doing an oxidation reaction. The reagents that would move you up the redox ladder are all oxidants. So as you learn chemistry throughout the course and you learn how to turn an alkene into an epoxide, that reagent is going to be an oxidant because it's moving you up from the 1 CZ bond level to the 2 CZ bond level. If you want to move down a rung of the redox ladder, you'll need a reduction reaction. If you want to turn a nitrile into an amine, you're going to need a reduction reaction moving down the redox rung from a nitrile from the 3 CZ bond level to the 1 CZ bond level of the amine. So when you learn that reagent, and that particular reagent will do a lot of these reactions, they will all be reduction reactions because it's a reductant. It moves you down the rungs of the redox ladder. So that's one kind of organic chemistry reaction. A redox reaction moves you between the rungs of the redox ladder. The second and only other kind of organic chemistry reaction is an acid-base reaction. An acid-base reaction moves you along a rung of the redox ladder. If you want to turn an alcohol into an ether that's the same rung of the redox ladder, you're going to have to use acid-base chemistry. You can't use redox chemistry because it's the same rung of the ladder. One of your reagents is going to have to be either an acid or a base. When you learn the reagents to turn a ketone into an acetal, you're going to be using sulfuric acid as part of that reagent because it's an acid-base reaction because it's on the same rung of the redox ladder. So as you learn the various reactions in this course, you can classify them as either redox reactions or acid-base reactions. Therefore, when you get to the exam and you're asked to predict the product of a reaction, and oh my goodness, I have no idea what this reaction is supposed to do, you can look at the reagents and say, this is an acid and a base reagent. I have to stay at the same rung of the redox ladder, and that really limits the functional groups that you can make. It directs your thinking in a particular line of thought that allows you to find the functional group that you need more easily. That's really it, friends. There's really only 2 kinds of organic chemistry reactions in all of organic chemistry. Let me give you some examples. Look at the reaction to turn an alkene into an alcohol. Notice the reagents are water and sulfuric acid. By recognizing sulfuric acid as the reagent, an acidic reagent, this must be an acid-base reaction, so we must be staying on the same rung of the redox ladder. And in fact, an alkene and an alcohol are both at the 1 CZ bond level. We can't move among rungs because we don't have an oxidant, we have an acid. The reagent MCPBA, however, turns an alkene at the 1 CZ bond level into an epoxide at the 2 CZ bond level. We're moving redox levels. MCPBA must be an oxidant. The reaction to turn an alkyne into a ketone involves sulfuric acid. It's another acid-base reaction, and an alkyne and a ketone are both at the 2 CZ bond level. Turning an alkyne into an alkane, however, moves us from the 2 CZ bond rung all the way down to the 0 CZ bond rung. So this must be a reduction reaction. Not only that, but this is a double reduction, moving from the 2 CZ level to the 1 CZ bond level, straight from the alkyne to the alkane. Which makes me wonder if maybe there's a reaction that can turn an alkyne just into an alkene, could only move down 1 rung of the redox ladder, a partial reduction of an alkyne. Stay tuned until you get to the alkynes chapter to figure that one out. We can even follow this along an entire reaction sequence. If I start with an alkene is at the 1 CZ bond level. I can add Br2, which turns it into a dibromide. A dibromide is not on our functional group list, but I see that there are 2 CZ bonds. This is at the 2 CZ bond rung. I must have done an oxidation. Br2 must be an oxidant. Maybe I keep a list of oxidants at the back of my organic chemistry notebook and a list of reductants at the back of my chemistry notebook. That way I can recognize them easier and know when I'm moving between rungs of the redox ladder. So if I can oxidize the alkene to the dihalide, I can come back the next week in my laboratory course and take this dihalide and turn it into an alkyne by adding NaNH2. NaNH2, sodium amide, is a base. It's a very strong base. If it's a very strong base, we must be staying at the same rung of the redox ladder, going from the 2 CZ bond state to the 2 CZ bond state, same rung. I can then stay at the same redox rung by turning the alkyne into an aldehyde using borane THF and sodium hydroxide and hydrogen peroxide. With that aldehyde, I can take this aldehyde and add chromic acid, going from the 2 CZ bond rung up to the 3 CZ bond rung. Chromic acid is an oxidant. This carboxylic acid at the 3 CZ bond level, I can react with ethanol and sulfuric acid. Sulfuric acid must be an acid-base reaction, must be staying at the same redox rung. This turns the carboxylic acid into the ester. So by organizing all of these reactions on this redox grid, we can turn this 1 CZ bond alkene into a 3 CZ bond ester using a couple of steps in sequence. Very powerful way to organize your reactions in organic chemistry. As you move throughout the course, I would recommend keeping a list of your reactions and organizing them by redox reactions or acid-base reactions. I would recommend organizing them by whether they make molecules at the 1 CZ bond level or the 2 CZ bond level. This way you can mix and match your reagents to make any functional group that you want. I would organize all of these on different sheets of paper in like a 3-ring binder. These are called reaction sheets. I have a video that I'll link to down below that teaches you how to make and use these reaction sheets for a study mechanism in organic chemistry. So how did I do? Did I convince you there are really only 2 reactions in organic chemistry? Leave me a comment down below. There are so many reactions we're going to learn in organic chemistry, we have to have some kind of organization system. I think this is a very good one. Have a great day, everybody.
I'm glad you're here with us for this training today. Check out these other videos in my playlists to see if there's anything else that can help you level up your ninja levels even further. As always, don't forget to like and subscribe.